Spanning tree of a weighted graph. Previously, when we were discussing finding the spanning tree for a non-weighted graph, all we had to do was find the subgraph that contained the least number of edges. The reason that was all we had to do was because in that case, all the edges were the same weight. They were all zero weight. So in that case, the least expensive graph was the graph that had the least number of edges. With the weighted graph, however, that's not the case, or that's not always the case. With the weighted graph, the least expensive graph is the graph that has the least combined weight of edges, which sometimes might also be the graph with the least number of edges, but also sometimes may not be. So, how do we go about finding this spanning tree? There are two ways to do it. The first way is called Prim's algorithm, named after the computer scientist Robert C. Prim. And what Prim's algorithm does is it takes the starting vertex and places it on the island by itself. It'll then repeatedly select the lightest edge that connects a vertex in the island to a vertex outside the island. Then that vertex that's outside of the island will become a part of the island as well. Here's what I mean. Currently, the lightest edge connecting a vertex in the island to a vertex out of the island is the edge connecting A and B. So B becomes a part of the island, and the edge connecting them gets put in an array list. Then we repeat. Currently, the lightest edge connecting in a vertex in the island to one outside of it is the edge connecting A and C. So C joins the island, and the edge connecting A and C goes to the array list. Next, once again, currently the lightest edge connecting a vertex in the island to one outside of the island is the edge connecting C and F. So F joins the island, and we store away the edge. The lightest edge connecting a vertex in the island to one out of it is the edge connecting F and G. So G joins the island, and the edge gets stored away. Rinse and repeat. The next lightest edge connecting a vertex in the island to one outside of it is the edge connecting F and E. So E joins the island, and that edge gets stored away. Rinse and repeat. The next lightest edge connecting a vertex in the island to one outside the island is the edge connecting E and D. So D joins the island, and the edge gets stored away. We now have all vertices in one island, thus indicating that the algorithm is complete. All edges that have not got traversed get discarded, thus completing the spanning tree problem. The other algorithm we could use to find the spanning tree is an algorithm named Kruskal's algorithm, named after the computer scientist Joseph Kruskal. And what Kruskal's algorithm does is it places every vertex in its own individual island. It then repeatedly selects the lightest edge that connects two vertices on different islands. So let's start. Currently, the lightest edge connecting two vertices on different islands is the edge connecting C and F. So we join those islands together. The next lightest edge is the edge connecting F and G. So those two islands become one. The next lightest edge is the edge connecting A and B. So those two islands become one. The next lightest edge connecting two islands is the edge connecting D and E. So those two islands become one. The next lightest edge connecting two islands is the edge connecting E and F. So those two islands become one. The next lightest edge connecting two different islands is the edge connecting C and A. However, before I move forward, allow me to make an important point. Notice that while the edge connecting C and A was the lightest edge connecting two different islands, it was not the lightest edge remaining. That distinction belongs to the edge connecting D and F, which was weight 16. However, that edge did not connect two different islands, which is why we did not select it. I make this point just to illustrate the fact that just because one edge is lighter than the other does not automatically mean that that edge will be a part of the spanning tree. So, going back to the algorithm, we see that the edge connecting C and A was the lightest edge connecting two different islands. So, we join those two islands, and then that edge gets stored away. We now have all vertices in one island, thus indicating that we're finished. All edges that never got selected get discarded, thus completing the algorithm.